So, hello everyone. So I'm Wang from University of Hong Kong. My presentation today is to provide a cyber-physical social perspective on future smart distribution systems. So I would like to acknowledge my four co-authors. Dr. Chen, she's working on social science in any system. Dr. Peng Yun Kang and Dr. Hu Shenli, they are working on cyber systems in any systems. And Dr. Qin Wen, he's from Alibaba, who is working on data analytics. This is the reason why five of us write this paper, Cyber Physical Systems. So for the transition of smart grid, we can see high penetration of distributed energy resources in distribution grid. We can see a large number of data connection, communication, and control devices. And there are 3D transformation in distribution systems. The first one is digitalization. A large number of smart meters and also control units are installed. And the second one is decentralization. Electricity consumers are more involved in decision makings instead of just passively consume electricity. And the third one is decarbonization. We need to accommodate more local renewable energy and enhance energy efficiency. So traditionally, we can say smart grids are cyber-physical systems, but we would like to emphasize that the whole distribution system should be of the human, by the human, and for the human. We need to focus on a massive number of electricity consumers, retailers, and other participants. And we need to consider human participants and their interactions in the decision loop. So actually, we can see deep fusion among humans, communication networks, and computers, and also other things. This figure shows 3 layers of distribution system. We have physical layer, they have power networks, power transformers, and other equipments. And on the cyber layer, we have communication networks, control centers. Maybe we have power line communication and also wireless communication or something like that. The second one is the social layer. It involves consumers, retailers, system operators. They have their own business models and they need to make their own decisions. So we can say they are decoupled, they are deeply decoupled in this process of power system planning and operation, business model, and its action interdisciplinary research, okay? So I would like to take some examples. For example, for a smart meter installation on the cyber system, the smart meter can help us to connect fine-grained smart meter data, energy consumption data. For the physical layer, the place to install smart meters should be well in line with household distribution and network topology. But for the social system, we have to consider the acceptance, consumers' acceptance of smart meter. For example, in UK, we put a lot of emphasis on the consumers' acceptance of smart meter. For example, for demand response, we need control signal transmission for to implement demand response. But we have to consider physical characteristics of distributing energy resources. Usually, we should also load the utility function of or wirelesses of consumers so that we can accurately model the demand response behavior of consumers. So from this simple example, we can see there's a deep decoupling relationship among cyber, physical, and social systems in distribution grid. So actually, there are a lot of topics. It's a very wide topics. In our paper, we just show several hot topics. For example, on the cyber physical system, we focus on distribution system monitoring and control, power system communication, networks dependencies, and also the potential application of 5G application. And for the cyber physical coupling, we focus on new technology adoption, for example, electric vehicle, renewable energy, and so on. And also the demand response limitation and also the impact of COVID-19. For cyber social coupling, we focus on social networks and the privacy protection and also data privacy and protection. So you can say there are several technical issues involves power engineering, communication engineering, social psychology, and data science. So for the first one, cyber physical coupling in distribution system actually is we know that as a two-way electricity flow and communication flow. So actually there are rich literatures on cyber physical coupling. For example, in our paper, we review the works about distribution system monitoring and control, especially for demand response monitoring, distributed networks monitoring, and also distributed energy resources control. The second one is the power communication networks independencies. Actually, you can say communication system support the control of power networks. Power networks provide energy supply to communication systems, so they are dependent with each other. So we need to analyze the cascading failures and also the cybersecurity of that. The third one is the potential application of 5G communications. Actually, there are many characteristics of 5G communication. For example, device-to-device communication, massive edge devices, or something like that. They can be applied to distribution systems. So the second one is for physical social coupling in distribution system. We can roughly divide it into micro social coupling, which is more related to energy policy. For example, for carbon neutrality policy, we need to reduce the carbon emission as much as possible when we make a decision. And the second one is a micro social coupling. It's more related to different participants or stakeholders, such as consumers, retailers, and system operators. So for example, when we develop distributed energy resources, we need to consider the acceptance and also cooperation of the social public to a large extent, okay? For example, here we need to consider three kinds of social acceptance. The first one, social political acceptance, is acceptance of key stakeholder of related energy policies. The second one is community acceptance, is acceptance of local stakeholders, for example, local resident or consumers. The third one is market acceptance, is the adoption of the level of actors in the distributed energy market. For example, here for the community acceptance and market acceptance, based on through market, we can provide compensation schemes so that we can enhance the communication acceptance of distributed energy resources. If we have a high acceptance in communication level, community level, actually there will be an increase of citizens' investment in the market. So they are deeply decoupled. So the next example is the influence factor and incentivize for electrical vehicle integration. Actually, the electrical vehicle integration contains two parts. The first one is the electrical vehicle itself. The second one is the smart charging systems. So we analyze the influence factors, the main influence factors for the adoption of electrical vehicle from technical perspective, financial issues, and the psychological aspect. And also there are some incentivize, for example, subsidized supplementary services or so on. That's similar for adoption for smart charging systems. So for the third one, social coupling distribution systems, actually we're focusing on electricity consumers. For example, what the consumer say in social networks, we call it social sensors, can be used for distribution system management, such as outage detection. For example, in this, we can say social sensors for distribution system. If there's a power outage, actually consumers will use social media to complain this kind of outages in Twitter, Facebook, or other social media. So this kind of social sensors can be used for outage detection and other applications. So the other aspect is for data privacy and pricing. We need to protect the privacy of different kind of stakeholders or participants because data can reveal this kind of information. But if the data are disputed and cannot be shared, how can we find the real value behind this kind of data? So we need to give the price so that we can incentivize sharing this kind of data. So that's another aspect of cyber social coupling in distribution systems. So lastly, if I want to mention some open research issues, I would like to mention that from three aspects. The first one is cyber system operation and planning. It's about cyber attack risk by reducing communications. Can we really reduce communications so that the cyber physical can be further enhanced? The second one is human behavior modeling. We know that cyber system and also physical system can be modeled by Maxwell equations, but human behavior cannot be modeled by any physical laws. Okay, so we need to develop integrated modeling approach for cyber physical systems, and we can implement human in the loop simulation and also backup power deployment for cyber systems. Actually, the last one is for data. For data supply chain, actually we have supply chain for some usual goods, but can we also establish a supply chain for data itself? Okay, so we can do data sharing, data storage, and also data pricing. And the second one is for social and technological data fusion. The last one is interactive machine learning smart grid, so that human can be included in the loop for data usage. Okay, so that's all my presentation. Thanks.